Assalamu alaikum. Okay, my name is Muhammad Noman Islam Khan, and this is lecture number 15 of our course, and we will be discussing the curve fitting today. Um, just a review of the previous weeks. Till now, we are able to complete the equations, one variable equation, and system of equations. We have deal with the linear system, non-linear system, okay, and now we will be starting the curve fitting. This will be an introductory lecture in which we will be try to learn what are the approaches available for the curve fitting and in which particular approach we will be heading. Okay, so just to, for example, start with an example. For example, we have a gasification process, and with the uh, I just took one of the independent variable as temperature. So with the varying value of the temperature, the hydrogen yield has been reported in percent as a 0.1%, 0.7%, 2.8%, and 3.1% at different temperatures. Okay, maybe I'm interested to find what is the possible hydrogen yield at maybe 30 degrees Celsius. Okay, or maybe what is the hydrogen yield at the uh, 80 degrees Celsius. Okay, so and also maybe I'm interested to find the hydrogen yield at the 100 and 20 degrees Celsius. Okay, so with these two things, actually what I'm trying to do is I'm trying to predict the value of a hydrogen within the data of the temperature from the 25 to 100 degrees. So these points lie between those. So these will be the interpolation. And for this particular point, which lies outside the domain of actually the values of the temperature, we will be extrapolation. We'll be using some extrapolation techniques. Okay. And one more thing that we may be interested is after the prediction of these values, that maybe I wanted what is the change maybe at 50 degree Celsius, or maybe at any of the temperature point, what is the change in the temperature, change in the hydrogen yield at different temperatures. Okay, and possibly there is one more scenario in which I may be interested to find the cumulative maybe hydrogen yield from maybe T naught to some Tm, maybe from 25 degree to 75 degrees Celsius. Okay, so for that I will be using the concept of the integration. So maybe from some T naught to Tn, I wanted a value of the hydrogen. Okay, so if I wanted to go beyond the prediction to the find the change of the hydrogen yield or maybe a cumulative value, I will be using another actually techniques. We'll see that in particularly in this lecture, how we're going to proceed about the prediction and then further about the uh, prediction of the derivative, a change or prediction of the cumulative actually value of some variable. Okay, so starting with this, let me just draw the first step that we are supposed to do. So we're starting with the two variables. One is the dependent variable, other is the independent variable. So for example, I have the temperature here and hydrogen yield here. Okay, you can just imagine it as maybe some independent variable x, and it can be some dependent variable y. Okay, so generally, let's assume that x and y are the independent variables which are involved. Specifically, that can be temperature and a hydrogen yield. So, first step in the data is always to try to plot that data to see what is the behavior of the data. So maybe I just Okay, for example, this is some plot, and now if I ask you what is the behavior actually that I see of the total data. So we have plotted the total data. Now I want its behavior. It behavior look like linear behavior. Okay, so maybe a linear line will be like this that I want to fit within this data. Okay, so the behavior is it's a linear behavior. So the consolidated actually behavior of the data, we will be able to see it once we plot it. Okay, that will be the consolidated behavior of the data. Now the point is maybe I just plotted another maybe behavior, then I'll come to the point. Uh, for example, if you see maybe this is some data, and if I just wanted some behavior that I can fit within this data point, maybe it will be some quadratic curve. Okay, so a degree 2 curve maybe I wish to fit within this data. And if for example I have took another case, so you see if this is some points of the dependent and dependent variable, then the behavior is look like an exponential one. Okay, so the thing is, once you plot your data, you will be able to see the behavior of your data being represented by any of the polynomial, or by maybe the exponential, that is you see a rapid change or a rapid decrease. Okay, so you can fit the exponential curves, or maybe the log curves. Okay, so it depends. Once you plot the data, you'll be able to see what is the total behavior of your data once you're able to plot it, that you can see it. We'll just continue with the first example, which is actually the first behavior, which is a linear behavior, and try to understand some concepts. So this is the state behavior that we see of the data. Now what I wanted is, maybe I wanted to fit a linear line within this data. Okay, so maybe I wanted to say, okay, L of x is equals to, so what is the equation of a linear line? Is simply a naught plus a1 x. Okay, so this is the linear line, that possibly the equation of the line I have just plotted. Okay, and you see this linear line is giving me the predictions. Okay, so we have this is the prediction curve, and the dots are my actual data. So if for example I plug x equals to x naught in this equation, I will be able to get a value a naught plus a1 x naught. Okay, now this L of x naught is the predicted value at x naught, and what is the actual value? For example, the actual value is, so if for example the points are x naught, y naught, x1, y1, so on to some xn and yn. Okay, these are, let's say, the points that I have plotted. So what is the actual value? Actual value is the y naught is my actual value. And if I ask you to find the error, what will be the error? So error will be y naught minus L of x naught. So that will be my error. Okay, so that is the error associated at a point x naught. And now if I just try to find maybe a value at x equals to x naught, it will be L of x1. Okay, so this is the approximate answer. The exact answer is y1. So if I just take a difference of the two, it will be my error associated at a point x1. Similarly, if I just continue till the last point, so I will get a predicted value at xn, and the actual value is yn. Predicted value is L of x. So the error associated at the final point will be yn minus L of xn. So that will be the error associated with each point. Now the thing is, if I ask you to calculate the total error, you'll say, okay, let's sum up this all error term. So the total error will be we have y naught minus L of x naught plus y1 minus L of x1 so on to yn minus L of xn. But you see, we always talk about the error in absolute term. The reason is, for example, the error at this point is 0.1 and error at this point is minus 0.1. So the cumulative error will be 0. Okay, so that's why it's a deviation. Deviation can be obviously predicted value can be up, predicted value can be down if my y-axis is giving me prediction. So it's a deviation. Deviation should be in absolute terms. So that's why we use the absolute sign to calculate the error. Okay, and it's called an absolute error. Now coming towards my line that I have plotted, for example, the error associated, I just calculated some error, and the error associated with L of x is a naught plus a1x, and error comes out maybe e naught. Okay, e naught is the error, or maybe e1 is the error that I got associated with this line. Okay, let me just call this as a line number 1. Okay, so at line number 1 I got the error 1. Now the thing is, when I say this as line number 1, okay, so I wish to find a line which comes with the minimum error. Okay, so if you see this data, in this data there is obviously the data is not going to change, so these dot points are not going to change. What's going to change is the line that I wish to fit within this data. Okay, so that is my linear line. So now to change this linear line, what can I change? I can change this a naught and this a1. Okay, by the way, in the language of the machine learning, this a naught and a1, which are responsible to change the prediction curve, are called hyperparameters. Okay, and so if I wanted maybe another line fit within this data, so this is maybe a line number 1, and line number 2 can be this line. This is line number 2. So if I got some line number 2, so it will be some a naught and a1, a different value of a naught and an a1. Let me just call it a naught bar and a1 bar. Okay, so it will come with some error e2, because the prediction with this curve will be different as compared to the line number 1. Okay, so we got error that is e2. Now the question is, we need to compare which error is the minimum. Okay, so that line will be the best fit line. So let me just write a statement, a remark maybe. A straight line with minimum value of the error, okay, maybe ei, is the best fit line. Okay, that is the best fit line, but so this may be a remark number 1. Remark number 2, follow up with this remark is to choose, okay, this line comes with the minimum error. I need to choose the value of A0 and A1 at which I'll got a good predictions. Okay, so it means I can minimize error, actually my error function, that is depending on A0 and A1, because if I change the value of A0 and A1, I got the different prediction. Okay, so and okay, do you got a question? Okay. No, you see, okay, we have got a question that if you change the value of x, we can't change the value of x because x and y are the data points. So we're not going to change our data, okay, but what we can do is we can choose a curve which is we trying to fit within the data, and that curve is a straight line. Okay, we see that our consolidated behavior of my data is a straight line. So let's try to fit a straight line. When I try to fit a straight line, I see a straight line can only be changed by two things, namely this a0 and a1. Okay, so this error function is depending on this a0 and a1. Okay, so my objective is to minimize this. How can I do that? I have the error over here. Okay, so let me now write what is the total error. Let me write that error in a form which is a0 and a1. So if you see this equation says y0 minus, so we got L of x naught. What is the value of L of x naught? This is a naught plus a1 x. So a naught plus a1 naught. Okay, so then we have y1 minus corresponding predicted value is a naught plus a1 x1 plus so on. We have yn minus a naught plus a1 xn. The point is that if you see this error, actually this error has some constant numbers which are xi's and yi's. Okay, they are some constant values because they are the data points. Now this a0 and a1 we need to choose in a way that this function have a minimum value. Now this is actually a problem of a two variable function, how to find the minimum value of the two variable function. If you see this equation, actually, so we have to find the minimum value of the error. Okay, I just need a space, so I'm okay, this is my okay, we'll come back to this. I'll replot it. Okay, if you see that error term has is a variable of two functions, which is a naught and a1. And let me just write in a summation form. This is I0 to n yi minus a naught plus a1 xi. Okay, because you got this from y0 till yn, so I is running from 0 to n. So this is a summation form. Now it is a two variable function. If you just recall from some of your previous course of the calculus, probably the vector calculus, you learn about finding the minimum value of the two variable function. Here we have to do what? We have to find the critical point first. Okay, obviously whichever are lying in the domain. Okay, we need to check the boundary conditions, or whichever is the boundary. Then we can apply on the interior points. If we got this as greater than 0, this at the critical points, then we try to find, okay, maybe we got a maxima or a minima. So what we are looking is actually we're trying to minimize this error function. So what we have to do is we have to take this f is actually my error function, and x and y are actually my a0 and a1. Okay, so to do this I have to take the partial derivatives. Okay, and I have to calculate the error. So now to calculate the error, if you see a difficulty over there, we have a absolute sign. Okay, so let me just write over here y is equals to mod of x. So if I just try to plot this y is equals to mod of x, what you will see is there is a corner at this point. If you got a corner at this point, the function is not differentiable. Okay, so it is not differential. You can see a minima is being occur at this point, but you cannot apply the second derivative test to find the minimum because it is not differentiable a point where this minima is lying. Okay, so what we can do is actually we can create another function by taking a square on the both sides. Okay, so mod of x square means x square, and let me just call this as z equals to x square. Now if I just plot z equals to x square, so it will be a smooth function. Okay, and the minima of z equals to x square is lying at the same point as the minima of mod x. So what we are interested is we are interested in finding that at which point the function is minimum. Okay, so now maybe we will not be able to do that task using this mod of x, which is the original function, but when we take a square of this value, okay, and then we apply the second derivative test, we will be able to get the minima of uh, the function z. Okay, so with this observation, okay, you see if you see this error function has the corners as at many points. Okay, actually whenever this term is going to be 0, okay, in absolute, we will got some corners. So there are many corners over there. So to overcome this, rather than considering this error function, we'll consider we'll take a square of this value. Okay, that will not impact at which point the function is taking a minima or a maxima. Okay, so we're not going to impact it, but we will be able to apply the second derivative test to find the minima or a maxima. Okay, the thing is, no, I'm not going much into the detail at this lecture. Okay, so we'll find um, a second derivative. We'll first find the critical points. Okay, then we try to evaluate them onto this actually combination, and we try to see it. We'll try to find the value of a naught and a1 which are coming from some critical point, the value of an a naught and a1 where this error function is minimum. Okay, once we find those values, we'll be able to find those values. We are going to say that I find a line which comes with the minimum error. So that choice of a naught and a1 that we're getting from here, okay, will be the best fit line. Okay, so this is a little observation. Okay, it's a part of a calculus. Okay, so we're not going over there, but what we're trying to conclude is a very important thing. Okay, let me conclude that over here. Um, so whenever we have this data that I just try to plot it, okay, initially, and I say, okay, uh, this is a rough plot of thing I already plotted, and if I just see a total behavior of my data, it is the linear behavior, and maybe this line is the best fit line that I'm able to do that, that I'm able to get that value of a naught and a1 at which we got a minimum error, so that will be best fit line. Okay, some L of x, which is this. Okay, now a property, an important observation is this: this straight line is does not passing through every observation xi yi. So we have this data xi, yi. Our data is this. This is our data, okay? And we are actually not able to find the uh, any curve which is passing through every point, because if I try to do that, that will be not a linear line. So I'm just saying, trying to see what is the total behavior of the data and trying to fit a line. So a critical observation is this L of x is not passing through every xi, yi, okay, I running from 0 to n. So this is a very critical observation, okay? So, um, but what we are actually getting from over here is we are getting the prediction at some xj's actually, okay, which obviously are not reported here. Maybe as I just started, for example, if it fit a linear line maybe within this data, so then I try to predict the value at 30, okay? So that this xj will be that 30 and an 80, okay? So we can do that with this linear line. Okay, this portion is actually coming with the more focused on prediction. So let me write more focused on prediction. So when you try to more focus on to the prediction, then you try to develop the curve uh, which will not pass through every point. So that's why there is a concept of the error that we calculated at every xi. Okay, at some xi will be able to pass through that. The prediction is actually passing through that data, but you see a deviation here. You see a deviation here. Okay, so I'm talking about this deviation. So this approach is the machine learning approach, okay? So this is a machine learning approach, and what we actually trying to do is we try to use one of the concepts of the machine learning, which is the linear regression, okay? So when we are actually more interested in predicting the value of the dependent variable, okay, so then our focus is majorly on to the prediction, okay, but there are more things that we need at times from the curve that we're trying to fit, which is maybe I wanted a change at a certain point, okay? So maybe I want to change at a 25-degree or a 50-degree or maybe at a 30-degree, okay, at which I try to predict it. So, and maybe I wanted to just sum up that information in form of the actually integral, okay? So to find the maybe a total yield, okay? So to do those things will be a different approach as compared to this one, okay? So if I am more actually trying to go beyond the prediction, and I also want to find the changes at the dependent variable happening when I am changing the independent variable, when I'm changing the temperature, or I wanted to accumulate the information, then that approach leads towards a thing which is a different as compared to this. And let me just start with the same thing by plotting some graph. So I'll say, okay, I'll try to. So for example, this is some a data point, okay? So my approach will be that I wanted to go from every xi, yi. So this is my data xi, yi. And I wanted to pass from every point, okay? My curve will pass through every point in the data which is xi, yi. Okay, if I try to do that, you see, maybe I got a maybe I got such a curve. Okay, now I am trying to fit a curve which is passing through every point. So this is a clear actually difference between the two approaches. In one approach, I see a total behavior of the data, and then I try to fit that curve. And in another, I try to pass through every time and see whatever the curve is going to be developed. Okay, so this approach actually help us better in the finding the derivative of the dependent variable, and in finding the integrals of from the data. Okay, trying to sum up the information from the data or finding the change of the data. Okay, so that approach will be leading from this particular idea. So by the way, if I just name some of the few methods into this particular approach, so we have regression models, okay, different regression models, exponential, okay, we have logistic models, okay, we have Gaussian process regression, GPR, we have support vector machine, we have tree models. There are different tree models. There are bagging and boosting models. Okay, we have artificial neural networks. We got a neural networks model. Okay, so if my focus is majorly about the prediction, then I will be using the machine learning models. Okay, which are famously bagging boosting models, Gaussian process regression, neural networks. These are some models that I'm trying to use. But if my focus is that I wanted to fit a curve that will pass through every point, okay, I will not seeing the total behavior of the data, but I'm trying to fit the curve that is passing through every point, then these approaches are more actually towards the numerical side, and which have the methods, namely Lagrange interpolation polynomial. Okay, famously they are also called LIPs. Okay, and we have Newton's divided difference formula. So there are different formulas. They are usually called NDDFs. Okay, we have a backward, forward, and central approaches. We have a cubic splines. Okay, so these are some methods that are more actually focused about this idea, and then they give a good result in terms of doing more actually observation on that curve. That is, we just try to take the derivative of that curve. Okay, we try to find the integral of those curves, so to find some properties that are connected with our problems. Okay, so that will be the approach of leading towards these methods, which is LIPs, Newton divided difference, and a cubic spline, specifically for this particular course. Okay, so let me just also draw some of the observation that are connected with these actually methods, which is, for example, if I have 2 points, okay, maybe I got some 3 points or more than 3 points maybe. Okay, I got many points. So when I am starting from this point, if I got only 2 points, because the question of fitting the curve will obviously come at least with the 2 points. Okay, so these models, what they do is actually they try to fit a linear curve. When you will give it 3 points, it will try to fit a quadratic curve. okay, passing through all the points. You see, a linear line can connect 2 points. A quadratic line will be a line where you a curve where you will allow one turning. Okay, you got parabolas. Okay, so you allow one turning. Okay, so okay, we have a question. Okay. Okay, so turning means actually, you see, if we have a first degree polynomial, which is a straight line, okay, so if you just take a derivative, the derivative is constant, okay, so if you got a constant gradient, it will be just a straight line. If you got a second degree polynomial, we have this curve of equation of such a curve, okay, and then if you try to take a derivative, it will be a1 plus 2a2x. And if you just equate it to 0, you'll got a point of x where the derivative is becoming 0. It means you're getting some maxima or a minima. Okay, so you allow one turning. And if you got a third degree polynomial, okay, so a third degree polynomial will be a polynomial where you can have two turnings. Okay, you see, such techniques will try to develop a method where you'll have two turnings. Okay, these methods will try to fit a cubic degree polynomial. Okay, and if you got a multiple points, there is an issue that comes with the higher degree polynomials, because if you're just increasing the order of the polynomial, uh, then you will allow a function to have the lot of turnings. Okay, and you see, you try to avoid maybe such a lot of turnings in the data. Okay, because there is some total behavior of the data that is also playing a role. Okay, we try to adjust that. So higher degree polynomials are not very much likable, because they give you a lot of fluctuation, actually too much amplitude within the given points. Okay, so what we can do is, for many points, maybe I can fit a linear lines to connect these points. So if I just use the linear lines, so this will is called the um, these small lines are called the splines. So we got a linear splines. Okay, we just connect our data with a linear line between the consecutive points. Okay, so that will be my small linear lines connecting together. Okay, so that will be my linear splines. But what you actually see in a linear spline is, and which is not very much good, is that there will be some corners. Okay, there are some corners, and at corners the functions are not differentiable. So the curve that I totally see from this point x naught till the point xn will have some problems at the corners. Okay, to avoid this, we maybe actually can have or maybe quadratic degree polynomials. Okay, so we try to fit some quadratic degree polynomials over here. Okay, so let me just try to, between 3 points we try to fit the quadratic degree polynomial. So that will be the quadratic splines. Quadratic splines. Okay, then we can fit the third degree polynomials between the given points. So between the given points that we try to fit within the data from x naught till xn. Okay, so maybe we can fit quadratic polynomial between the two variable, or we can select actually this third point, and we can fit the quadratic polynomial between these from x naught to x2, maybe by just avoiding x1, but our curve will be passing near this x1. Okay, so we can have also the cubic splines, and in the cubic splines, between every 2 points, actually we try to fit a third degree polynomial. Actually, you see, a third degree polynomial will have a lot of actually variation, so we can pick any portion that can be fit between the 2 points. So that will be called the cubic splines. So this idea is a better idea if you have a lot of data and you wish to fit um, and try to avoid the higher degree polynomials. What you can do is you can put the splines between the consecutive points. Okay, so in that, the cubic splines are much used points. They have a good efficiency, and they lead better along with the first, second, third degree polynomials, generally speaking, towards the numerical differentiation and numerical integration. Okay, so they will lead better towards these ideas over there. So our actually course will be more focused about these concepts, because we will be leading towards the numerical differentiation and numerical integration. Okay, so just to conclude, actually, these two approaches. So we got two approaches of the curve fitting. Either we want more focused towards the prediction, or we are actually wanted to go beyond the prediction and finding maybe the changes in the curve, try to find maybe a derivative integrations of the curves. Okay, so so we got these two approaches. So in these two approaches, there are different methods. One is more focused about the machine learning model that we usually see nowadays. Okay, and on other side we have the Lagrange interpolation model, polynomial. Sorry, we have a Newton divided difference formula, and we have cubic splines. Okay, so we'll be touching these topics in the coming up lecture, and we'll have one lecture of the machine learning and specifically a regression model, and we'll try to see a gradient descent method in that particular lecture. Okay, so any questions? Okay, good. So now we'll see in deeply, actually in detail, about the curve fitting in the coming up lecture. Thank you so much.